In Lecture 7 of Electrical Fundamental, we will focus on Thevenin's theorem. We will precisely determine two critical values of Thevenin's theorem, VTH and RTH, Thevenin's voltage and Thevenin's resistance. And we will also look at the topic of how do we measure the total resistance between two pair of nodes in a resistive network. And finally, we will close the lecture by investigating and determining how much power can we transfer from a system to a load, and what needs to be done to have the maximum amount of power from a system that is transferred to a load. And that will complete the lecture. In a nutshell, Thevenin's theorem, as explained in this box, is a technique. It's an analytical technique used to simplify a complex circuit. So a circuit is referred to as complex when it's no longer just a series circuit or just a parallel circuit. It's a combination of series and parallel components that are connected together. And we could simplify a circuit with only one source in one resistance, like we just showed on the previous slide, where you have your VTH and RTH, and then you connect your load between the two nodes, nodes A and B. So the question is, how do we simplify this? How do we go from this complex circuit that is hard to solve to a simpler circuit that is much easier to solve? This is kind of the essence of what we will do today. So if you look here, you have two boxes. You have this shaded area. This part essentially is the system of the circuitry for your system. And after the nodes A and B, you have the load that is connected to the system. Equivalently, if we look at the simplification of the circuit, we look at the Thevenin equivalent circuit. So this is known as Thevenin's equivalent circuit. This entire complexity of the system is simply reduced by only two components that are connected in series, a source and a resistance, and between the two nodes, node A and B, you connect your load. And certainly just by looking at it, it is much easier to solve this circuit as opposed to the other one. Now the question that arises at this point is, well, how do we determine these two values, the VTH, Thevenin's voltage, and RTH? How do we find them? Well, this is essentially will be the focus of today's lecture. So like we said, VTH stands for Thevenin's voltage and RTH is Thevenin's resistance. And we'll see that on the next slide, the recipe for finding VTH and the recipe for finding RTH. Let's begin by finding VTH, Thevenin's voltage. So let's take the previous example that we saw. And like we said, this is a complex circuit. And we want to know what is the recipe for finding VTH. Step number one, we remove the load. So we had a load here between A and B, we simply remove it. Step number two, we determine the voltage between nodes A and B. So this is the next thing that we ought to do. And this voltage that we determine, this is essentially our VTH. This is Thevenin's voltage. It has also another name. It's the open circuit voltage of this circuit. And we essentially could use some of the techniques that we saw previously. Ohm's law, KVL, voltage divider rule, KCL, current divider rule. So for that, if you want a refresher, you could always go back to the previous lectures from lecture 1 to lecture 6, and then we've discussed some of these topics. So let's try to do this. So what we could do is we see loops. So we see two loops. We could essentially just write the KVL for each loop. And this is what we get. So essentially we have two equations with two unknown, I1 and I2. And we could do some analysis here. We're not going to do it here. I just wanted to show you the steps that needs to be done. But essentially, if we work the details, we could find I1 and I2. And once we find both of these variables, we could then determine the voltage VTH. And the voltage VTH is simply this resistor times this current times current I2. So R4 times I2, that gives us VTH. Don't forget that R5 is meaningless in this case. There's no current that flows into R5, and therefore this is the VTH that we obtain. In lecture number 6, we solved it using a slightly different method, but in a nutshell, this is the approach. Now that we have VTH, the next thing that we need to do is determine RTH. And for RTH, what we do is we go back to the original circuit. We simply bring it back again here, and we go through the steps. These steps are not, they're different, and we begin from the circuit here. We don't look at the previous circuit. We begin from zero from the original circuit. So step number one, we remove the load. So this load, we simply remove it, we get rid of it. Step number two, we replace the voltage source by a short circuit. If on the other hand we had a current source in here, we then replace it by an open circuit. At any rate, this is what we have. So we replace it by we have a voltage source, so we replace it by a short circuit. Okay, so this basically just becomes a wire instead of the source here. Step number three, we then obtain the resistance between node A and node B. So if we have a DMM and we want to measure the resistance, we simply put it between A and B and we measure the resistance of this resistive network. So the question is, how do we obtain this? And that's it. Once you get this result that you obtain is your RTH. So the question is, how do we do this? We have to do this gradually. Since we are beginning, we want to look at RTH between these two nodes, right? The resistance between A and B, resistor RAB is equal to really RTH. We generally look at it from the other end of the circuit. We begin from here and we move all the way back to the nodes A and B. So if you look at this, you look at this yellow shaded area, R1 and R2, if you look at them, they are both connected in parallel with each other. So we could simply have some resistor RA, and we simply write that R1 is in parallel with R2. Don't forget these two bars. We saw before that these two bars mean that two resistors are in parallel. And so now this yellow box can be simply, we can simply refer to the resistance in the yellow box as RA instead of using R1 and R2. Next, what we do is the result that we got, this RA that we got with R3, they are connected in series. So we simply add them together. The next thing that we do is we notice that the result that we got, which we called RB, and R4, they are in parallel. This is what we have, and we call it RC. And finally, the result that we have, RC, which is all this thing here, with R5, they are in a series, therefore we add them together, and this is what is our RTH. So if we work backward and we put everything together, the final result that we get is this. This is the final result that we get. Be careful here with the brackets. The brackets are very critical. It gives us a sense of how to do the computation of this expression. And this is the overall expression, right? So essentially we have R5, this one here, plus RC, and we said RC is RB in parallel with R4. So this is your RB in parallel with R4. RB is RA plus R3. This is our R3. And our RA is R1 with R2. So this is the final expression that we get. In the previous slide, we determined the total resistance between node A and B, and as we said, this is the Thevenin's resistance, and so we got this expression here. So one thing that one should realize is if you have an expression, you could right away obtain the circuitry related to this expression, or else if you have a circuitry, you could obtain the mathematical expression. So they are really interchangeable. You could go from circuitry to equation or from equation to circuitry. At this point, we determined the equation for this circuitry, and we could just now test it, see how it works. When you are asked to compute from an expression, what you do essentially is you work from the innermost bracket and you work all the way to the outer bracket. So you begin here, then you do this bracket, then you do the third bracket, and then you add it to R5. So let's just do this in an example. So in question 1a, we ask you if all the resistors have an equal value of R0. So all the resistors have an equal resistance, let's call it R0. What would be the Thevenin resistance? What would be this total resistance here? So we could simply rewrite this expression, and instead of writing R1, R2 all the way to R5, we simply put R0 everywhere. And like we said, we work from the innermost bracket all the way to the outer bracket. So here we do R0 in parallel with R0. So when you have two resistors of the same value, we've seen this in previous lectures, it simply becomes half of it. So if you have, let's say, I don't know, a 5 kilo ohm resistor with another 5 kilo ohm resistors, they are in parallel. The result that you get is a 2.5 kilo ohm. So R0 in parallel with R0 is simply R0 divided by 2. Then the rest you simply write it. So now we have R0 divided by 2 plus R0. If you want to add them, you want to make sure that the bottom, they have the same denominator. So if we put 2 in the bottom, 2 on top, you'll have 3 R0 divided by 2, which is basically 1.5. So this is what we get in parallel with R0. So now we work this bracket. So this is what we have. We have a resistor, 1.5 R0 with R0, and they are in parallel. So at this point, what you need to do is you need to invoke the expression that we saw before. When you have two resistors in parallel, you multiply their values on top and you add their values in the bottom, right? So let's just do that. So essentially, we do 3 R0 divided by 2 times R0. In the bottom, we do 3 R0 divided by 2 plus R0. What this essentially gives you is, maybe I could just write it so you can see what's going on. So we have 3 R0 squared, right? So you multiply these two together, divided by 2, and in the bottom we have, so if we put them with a common denominator, you put 2 here, you get 5 R0, and so it's really divided by 5 R0 over 2. And when you divide, you essentially multiply the reverse. So now you basically get 3 R0 squared divided by 2 times 2 over 5 R0. 2 and 2 cancels. R0 with R0 cancels. So now we have 3 R0 divided by 5. This is the result that we got. So all this bracket will basically equals this. Okay, so let's see what we get here. So like we said, we got 3 R0 divided by 5 plus R0, and now you could also put them with the same common denominator. So you could put a 5, let's say here, and a 5 here. So now you have them with a common denominator. You could add them. So 5 plus 3, that gives us 8 R0 over 5. So let's see if this is what we got. 8 R0 divided by 5. And 8 divided by 5, that gives us 1.6 R0. So we got the total resistance, RTH, between node A and node B if all the resistors are of the same value to equal 1.6 R0. Okay. Now in question 1b, we say, what if R0 is equal to 1 ohm? What would be RTH? So if it is 1 ohm, you simply multiply 1.6 by 1, and the result that we get is 1.6 ohm. Question number 2, we are interested to find the total resistance of this resistive network. So we're giving you this setup, and we ask you to find the total resistance between the different pair of nodes. So let's go through it, and hopefully this will make better, you'll understand better how this is done. So question number 2a, we ask you to find the total resistance between all possible pair of nodes of the circuit setup shown below. So when you are given such a network, don't assume that the total resistance will be the same everywhere. It always depends on the two nodes where you do the measurements. So if you measure the resistance between node A and B, it doesn't necessarily mean that it's the same resistance between node A and C. And it doesn't mean it's the same thing as between node B and C. So it always depends on which two nodes you are considering when you measure resistance. So let's see how to find how many possible ways can you measure total resistance. So the approach is you could certainly use the skill that you have from probability and statistics, where you do n choose k. So in this case, you have n, the total number of elements. So the total number of elements is the total number of nodes that you have. So 1, 2, 3, 3, and you want to choose 2. So you want to do a 2 combination. So this is a combinatorial expression. So 3, choose 2, and what you do is you do 3 factorial on top, you do 2 factorial on the bottom, and 3 minus 2, 1 factorial on the bottom. That gives you 6 on top, so 1 times 2 times 3, that gives you 6, and in the bottom you have 2 times 1, so that's 2, 6 divided by 2, that's 3. So there are 3 different ways by which you could do measurements. This is not necessarily necessary to do every single time you have these type of resistive networks. Sometimes you could just observe that there are 3 ways that you can measure resistance by simply observing it, right? So you could measure between A and B, you could measure between A and C, and you could measure between B and C. So right away you could figure out the 3. But putting it in an expression is always useful. It's always kind of it's a good way to make sure that you didn't do a mistake. So let's say we give you a resistive network where you have, I don't know, 5 nodes, right? So you do 5, choose 2. So you do 5 factorial divided by 2 factorial, 5 minus 2, 3 factorial, and then you do all that. So in this case, we only have 3. So 3, choose 2, and the result that we got is 3 possible ways that we could measure resistance between node A and B, between node A and C, and between node B and C. So let's just do that so that we could answer question number 2A. So let's look at what happens between node A and B. How do you get the resistance between node A and B? So if you were in a lab, you simply connect a DMM, a digital multimeter, and that will give you the result for the resistance between node A and B. But in this case, we do not have a DMM, and we want to have the capacity to find this analytically. So one approach would be, and this is the smartest approach to do it analytically, is to connect a dummy source between node A and B. So in this case, this is your dummy source. You have the plus on top, you have the minus in the bottom. The polarity doesn't really matter. You could flip it, you'll get the same result as well. But in this case, let's just consider this polarity here. You do the trace for the current, and this will help you figure out what is the total resistance between node A and B. So let's just do it together. So let's just do the tracing of the current together so you see how this is done. So just give me a moment here. So this is your plus, this is your minus. Current leaves the source. It comes to this node. Part of it will go to resistor R2. Part of it will go to resistor R1. It then moves into resistor R3. It comes to this point. It merges back again, and it goes to the source. So simply by looking at it, you notice that R1 and R3 are in series, and then the result that you get is in parallel with R2. So this is essentially what you get, right? So R1 and R3 are in series, and the result that you get is in parallel with R2. So let's then look at the next one. What happens between nodes A and C? So between nodes A and C, if we connect a source, so a dummy source here, this is your plus of it, this is a minus. Do the path for the current comes in here. Part of the current goes to resistor R3, into resistor R2, into resistor R1, it merges again, and it goes back again to the negative side. So if you notice in this case, R2 and R3 are in series, and the result that you get is in parallel with R1. So let's see. So that's exactly what we got, R2 and R3 in series, and the result that you get is in parallel with R1, and that gives you the total resistance between node A and C. So let's look at the third one that we have, and it is, we want to find the total resistance between nodes B and node C. So we put a dummy source between B and C. This is the plus, this is the minus. It leaves like this. This is the, it moves like this. It comes to this point. It goes into resistor R2, into resistor R1. It goes into resistor R3. It merges again, and it goes to the source. So if you notice here, R2 and R1 are in series, and the result that you get is in parallel with R3. So let's write an expression for it, and this is what we get.
So R1 and R2 are in series, and the result that you get is in parallel with R3. So notice that the resistance is not the same. So if you measure the resistance between A and B, you got this. If you measure the resistance between A and C, A and C here, you got this. And if you measure the resistance between B and C, you got this. So you do not get the same result. The results are different. So this is kind of the interesting observation that you should realize is that number one, when you measure resistance, it's always between two nodes. Number two, simply by looking at a resistive network, it doesn't necessarily mean you'll get the same resistance by looking at it between this different type of nodes. You might get different results, and that's what we observe here. So at this point, we've answered question 2a. Let's move to question 2b. We ask you in 2b if all the resistors are equal to R naught. So let's say all the resistors, R1, R2, R3, they're all of the same value. So R1 is equal to R naught, R2 is equal to R naught, and R3 is equal to R naught. What would be our total? So notice if all the resistors are the same, the total resistance everywhere will be the same. You'll have an R naught on top, and you'll have a 2 R naught in the bottom. In here, R naught on top, 2 R naught in the bottom, R naught on top, 2 R naught in the bottom. It's not really in the bottom, it's in parallel with R naught. So let's just plug in the value, and this is what we get, right? So what we get is the following. We get essentially R naught in parallel with R naught plus R naught. That becomes 2 R naught. So you have R naught in parallel with 2 R naught. And now when you parallel these two, you multiply R naught by 2 R naught. And in the bottom, you do R naught plus 2 R naught. That becomes 2 R naught squared. And in the bottom, you have 3 R naught. R naught with the square is canceled. So you eventually get 2 R naught over 3. Or if you will, you could simply get 0.67 R naught. So that answer is B. In C, we tell you if all the resistors, R1, R2, and R3, are of the same value and they all are equal 1 ohm. What would be the total resistance? Well, you simply put 1 in here and you get a total resistance of 0.67. So the resistance happen to be the same when they are all of the same value. So if all the resistors are of the same value, measuring it between A and B, between A and C, and between B and C will give you the same result. This doesn't necessarily mean it is the case all the time. You have to show it, right? It doesn't necessarily mean it's going to be the same. So if I give you any other type of resistive network and I tell you all the resistors are equal, it doesn't mean the total resistance will be the same by looking at it from different nodes. It just happens to be the case here. Question number 3, we give you the following question. So it has 3 parts. So let's read it together. Simplify the circuit below using Thevenin's theorem. So if you look at this circuit, the circuit is not so bad. One could in fact solve it without using Thevenin. But in this question, we ask you to solve it using Thevenin theorem. So first thing first is you need to identify where the output terminals are. And you could do that by noticing where the load is, and then this will let you know where the output terminal is. Quite often in an exam, we'll identify the output terminal. So this is terminal A, this is terminal B, and the load is connected to it. So if you see, the load is not even numbered as RL, it's R3, but rather RL. L for load, and then the system is here. This is your system that is here. So you want to change this system into a Thevenin equivalent circuit with only one source and one resistance. So let's go through the steps here. Question A, what is Thevenin voltage? This is what we want to find first. B, what is Thevenin's resistance? So like we said, you need both of them, VTH and RTH, to build your Thevenin equivalent circuit. Once you have that, you connect the load to it, and then you could measure whatever you're looking for. So let's go through A, B, and then we'll move on to C later on. So like we said, we want to change this circuit into a Thevenin equivalent circuit. So this is the Thevenin equivalent circuit. You have your source, you have your resistance, and then you have the load that is connected to it. So the question is, how do we find the voltage? We've already discussed how to find the voltage, Thevenin's voltage. There are 2 key steps. Step number 1,
is we remove the load, so we get rid of the load. And step number 2, we apply whatever techniques we know, so Ohm's law, KVL, KCL, current divider rule, voltage divider rule, to find what we're looking for. In this case, if we remove the load and we want to find the voltage between these two nodes, we can simply use voltage divider rule. Essentially, we want to find the voltage across R2. So you remove the load, and then we want to find the voltage across R2. And this voltage across R2 will be our VTH. Okay, so let's do that together. So we could use the equation for voltage divider rule. We put the key voltage, which is the source voltage, which is 12 volts here. We put R2 here, and then the ratio of the total resistance, this one with this one, right, in here. So let's just plug in the values. So we have 12 for the source, we have 27 for R2, we have 10 for R1, and 27 for R2. So everything is in kilo, so we don't need to write kilo. The top will be in kilo, the bottom will be in kilo. It's a ratio, so they're going to cancel each other. And then we multiply by 12. So let's see what we get. We eventually get a VTH of 8.67 volts. So we got A. This part is officially completed. Let's move on to B. So on the previous slides, we determined VTH, and the value for VTH that we got is 8.76 volts. So a value here of 8.76 volts. And now what we're looking for is really RTH. We want to determine what this value is. To determine RTH, we go through the process and what we discussed before. So the recipe for finding RTH. So as we know, the process is straightforward. First thing first, we go back to the original circuit. We remove the load, we get rid of it. Then we short the voltage source. So we replace this by a short, and we find the total resistance between the output terminal. So if we remove the load, we short the source, we'll essentially get simply R1 in parallel with R2. So if we do that, this is what will give us our value for RTH. So simply R1 in parallel with R2. R1 is 10K, R2 is 27K. So we essentially just multiply R1 with R2, and in the bottom R1 plus R2. And if we plug in the values, this is 10 times 27, and 10 plus 27. This gives us 7.3 kilo ohm. So now we have RTH as well. It is 7.3 kilo ohm. At this point, we essentially have our Thevenin equivalent circuit. If you prefer, we can also annotate the circuit, so we could simply write it so it's no longer a question mark. It is really 7.3 kilo ohm. So we have the Thevenin voltage, Thevenin resistance, and we could simply find the information that we're looking for. We know the load is 68 kilo ohm. 68 kilo, and at this point we're looking for some information. We're looking at what is the voltage VL here of the load, and what is the current IL that goes through the load. These are the things that we're looking for C in C. So let's go through the motions and do that. So find the voltage and current using voltage divider rule in Ohm's law. So we can certainly do that. We have the voltage, we have this resistor, we have the source, we have this resistor. We simply want to know what is the voltage here and what is the current that goes through it. So let's do that. We could simply use a voltage divider rule. The value that we have for VTH is 8.76 here. We put on top RL, this is what we're looking for, the voltage that is consumed by this load, and the total resistance, which is 7.3 kilo plus RTH, which we found to be 7.3 here, RTH, and 68 is the load. This is what we do. We do the ratio, and that gives us a value of 7.91 volts. Okay, so VL, the voltage of the load, is 7.91 here. The next thing that we need to do is find IL, so the current that flows into the load. And this, we could simply use Ohm's law. Right? So we have the voltage, we have the resistance, we can simply find the current through Ohm's law. And this is what we're doing, 7.91 divided by 68K, and this gives us 116 microamp. And now we have everything that we're looking for. Okay. Question number 4 is very similar to question number 3. The only difference is the circuit is different, but the same type of question. ABC. In A, we want to find VTH, RTH, and we want to find the voltage across the load and the voltage through the load. So let's go through the motion and do this. Let's begin by finding VTH. So for VTH, what we do is we, again, do the same recipe. We remove the load. And once we remove the load, we want to find the voltage across these two terminals, right? So let's just show you exactly what we're doing. Essentially, we are removing this here. This is gone. And then we find the voltage here. This is VTH. Right? This voltage across these two terminals will be VTH. Now, of course, if you have the circuitry, once this load is removed, the current will flow like this. It will go through R1. It will pass through R1. It will go to R2. And it will go back again to the source. This resistor is meaningless. There's no current that will flow to it, right? So this will be a useless resistor. So in reality, VTH is really equal to V2, the voltage here. This is V2, right? The voltage across resistor 2. So VTH is really equal to V2. And to find V2, what we could do is we could apply voltage divider rule. Okay, and that's what we did here. So VTH is equal to the source, Vs, and then we do a ratio of the resistor of where the voltage we were interested to determine, R2, and the total resistance, R1 and R2. Be careful here. This is only, the total resistance is just this one with this one, not R3. R3 is meaningless, like we said in this circuit. There's no current that flows to it. So then we just plug in the values. We have 12 volts. We have 2 kilo on top. We have 1 plus 2 kilo in the bottom. And this gives us the following ratio. So we have 2 divided by 3 times 12, and this gives us 8 volts. So VTH is really 8 volts. Okay, so at this point we have VTH. We know that the value for it is 8 volts. And what we are looking for is really to find RTH. So this is 8 volts. This, we still don't know what it is. So for RTH, we go back to the original circuit. And what we do is we go through the process of finding RTH. So the process to find RTH is, number one, to get rid of the load. Again, so to remove the load, and then to short circuit the voltage source. So this, you short circuit it, you remove it, you simply replace it by a wire, and this is our reference point. And we want to find then the resistance between this node and this node, right? So let's maybe annotate them, node A and node B. And the resistance between node A and B is what will give us our RTH. Okay, so in reality, when you want to find the resistance between these two nodes like this, you begin from this side, from the opposite side, and you move forward to the output terminal. So if you notice, we really have R1 and R2 that are connected in parallel, and then the result that you get is in series with R3, and this will give us our Thevenin Thevenin resistance. So let's see that. This is exactly what we said. So it's really this resistor with this resistor that are in parallel, and then the result that you get, you add it to R3, and this gives us RTH. So now we could simply plug in the values for it. So R1 is 1 kilo ohm, R2 is 2 kilo ohm, R3 is 100 ohm. So be careful, put everything in kilo, and so that's why for R3 we will write it as 0.1 kilo. So you have 1K in parallel with 2K. So we do this, the process of putting two resistors in parallel. So 1 times 2, 1 plus 2, plus 0.1 kilo ohm for 100. And the result that we get is 767 ohms. So this gives us our RTH. So at this point, we have VTH, we have RTH. What we have left is really to find the voltage here, the voltage VL, right? The voltage across the load VL, and the current through the load IL. This is what we want. And this we just found, right? So this is 767 ohms. So to find VL and to find IL, it's really straightforward. We have a simple circuit. We have the Thevenin circuit to do that. And we could use the voltage divider rule. We have the source, the Thevenin's voltage source, which is 8 volts here. We have the load, which is the 1 kilo ohm here. We have RTH, which is 767 ohm, and 1 kilo ohm, and we simply plug in the values. So 8, and we do a ratio of 1 over 0.767 plus 1, we get a result of 4.53 volts for the load voltage. For the current, we could use Ohm's law, and we have the voltage, 4.53. We have the load resistance, 1 kilo ohm, and this gives us 4.53 milliamps. So now we saw really two examples of how Thevenin, one could reduce a complex circuit into a Thevenin circuit and then get the relevant data from that simplified circuit, from the Thevenin circuit. Question number 5. So let's read the question and try to make sense of it as we go along. So a signal generator has an output voltage of 2 volts with no load. So let's see what we mean by that. So this is a signal generator. It's just a device that generates signals. We've seen perhaps this in the lab that we have, and it generates an output voltage of 2 volts. Right, so the output from this generator is 2 volts DC with no load. When a 600 ohm load is connected to it, so we connect a load to this signal generator, the output drops to 1 volt. Right? So this is what we get. We connect a load. The output is no longer 2 volts. It becomes 1 load. Right? When a 600 ohm load, so the resistance, so it doesn't have to be a resistor, it could be any type of device that you connect to it. It has a resistance of 600 ohms. The voltage drop is 1 volt. The question that we ask is, what is Thevenin's resistance of the generator? So you could think about it this way. If this is 1 volt that is consumed here, overall you have 2 volts. Right? The system has 2 volts. 1 volt is consumed by this load, and basically 1 other volt is also consumed by the internal resistance of the signal generator. So because the voltage is split equally between them, you expect the internal resistance of your system to be exactly similar to the load. So we expect it to be 600 ohms. Okay, so this is, you could think about it from a circuit point of view. From a circuit point of view, you have a load of 600 ohms and it consumes 1 volt. Overall, you have 2 volts. You put a load, it has 1 volt. You have one other load that is consumed somewhere. Where would it be consumed? It would be consumed inside by the internal resistance of your system. So you could think about it as your RTH, if you will. And therefore, the question is, what should be the value of this resistance? It should be the same value of this one, because if this one takes 1 volt and this takes 1 volts, this resistor should equal this resistor. So it has to be also 600 ohms. And that's basically what we get for the result, which is B. The final topic that we have left is the concept of maximum power transfer. This is the formal explanation. It is the maximum power that is transferred from the source to the load when the load resistance RL is equal to the internal resistance of your system. So let's say, look at this circuit. This is on the left, you have your system voltage and your system internal resistance, and then you connect a load to it. Now here we call it VTH and RTH just because today's lecture is about Thevenin, but it could also be called VS and RS, or it could be called VN for and RN for the internal resistance of a system, and we connect a load to it. And we want to squeeze as much power from the source to the load. And we want to know when can this happen. And if you go from the definition, this is true when the load resistance is equal to the internal resistance of your source. So if RL equals to RTH, you will get the maximum power at the load. That's basically the key thing that we want you to capture from this slide. Now we'll explain to you why this is true. So let's use the voltage divider rule to find the voltage across this resistor. And this is what we get. And if we compute the power, right, using Watt's law, we could compute the power of this load. So we use this voltage that we got, squared divided by RL. We simplify, we get this. And if we use this to plot the relationship between PL, so this line here is PL, the y-axis, and the x-axis is your RL. And we computed, we get this kind of graph. If you notice, you get the maximum value at this point. Now you might ask, what is this point? Well, this point is really the value where the load equals the internal resistance. So when the load equals internal resistance, you get the maximum amount of power at your load. If the load is less than the internal resistance, you don't get the maximum power. You're on this red area. If your load is bigger than the internal resistance, you don't get the maximum. The magic number is really here. When the load equals the internal resistance, you get the maximum amount of power. And we could in fact compute this amount of power. But we could say, well, what is this amount of power? Well, if you take this equation and you replace the load by RTH, right? Everywhere you see RL, you replace it by RTH. You put it in here and you get the expression. So this is really what you get here, the maximum amount of power. Okay, but if you ask me, what is the key thing from this slide? Really to know that RL should equal the internal resistance of the system. When this is the case, you get the maximum amount of power at your load. So let's try a question related to the maximum power transfer. So this is question number 6. What is the power delivered to the matching load? So if you notice, we have the circuit that is shown to us here. This part here is our system. So this is the system, and this is the load. Okay, and we have two nodes, right? We have node A and node B, and this is where you differentiate between the system and the load. This is the border between the system and the load. And we're saying, we're asking you, what is the power delivered to the matching load? So matching, in other words, what it means is that it matches. It has the same value as the internal resistance. If the internal resistance is 50 ohm, so their load is equal the same value as the internal resistance, and it is also equal to 50. Okay, so if the load is 50 ohm and the system has 50 ohm, this guy here will get half of the voltage, right? It will get 5 volts. And this one here will get the remaining 5 volts. The remaining 5 volts will be here. And now the question is, well, how much power does this one get? What is this power that it gets? And basically this power that it gets is the maximum power because the resistances are matching. Now the load has the same value of resistance as the system. So we could just use Watt's law to compute the power at the load. So from Watt's law, we could just use a voltage divider rule. In fact, you don't need to use voltage divider rule. Just from inspection, because the resistance are equal, it's like a pizza. This guy will eat half of the pizza, the other guy will eat the remaining half. We expect this to be 5 volts, but you could use voltage divider rule to find out that it is indeed 5 volts. But you see here, we just did it straightforward without this. Now that you have your 5 volts, you could then use it in Watt's law and to determine the power that is dissipated by the load. And if we do that, we just take the 5, we square it, we divide by 50, we get 0.5 watts, or if you will, 500 milliwatts. And that's really the power, the maximum power that is delivered to the load. Question 7, this is a multiple choice question. Maximum power is transferred from a fixed source when the load resistance is 1/2 the source resistance This is not true, so this is wrong. The next one is when the load resistance is equal to the source resistance. This seems correct, but let's read the rest. When the load resistance is twice, that's not true as well. None of the above, that's also not true. So the answer should really be B. Let's verify. This is exactly it. So that completes today's lecture. Thank you.